So here let's take a look at another common pattern in synthesis. And in this case, we're going to start with a terminal alkyne. So in this case, specifically acetylene, which is terminal on both sides. And we'll know that we could make a carbon-carbon bond on either side or on both sides. And in this case, we'll start off with the first one, and we'll just simply add a primary alkyl halide, and we'll do SN2. So, and we'll have formed this new bond right here. So, and with this terminal alkyne, we've got some options. We've learned that we can make a new carbon-carbon bond on the other side using just another alkyl halide. We could add a ketone or aldehyde, and the carbon we attach to becomes an alcohol. So, or we can add an epoxide, and not the carbon we attach to, but the next one over is going to be attached to the OH of the alcohol. So, but you've also learned some other alkyne reactions. With a terminal alkyne, you can do Markovnikov hydration, which tautomerizes to form a ketone. You could do anti-Markovnikov hydration, and the enol that formed again tautomerizes to form an aldehyde. Or you could do ozonolysis, which would chop off one carbon, but would do oxidative cleavage and cleave that triple bond in half, if you will, forming a carboxylic acid on one side and then carbon dioxide on the other side. So you'd end up with one fewer carbon than the previous step. And then keep in mind also, if you do form an internal alkyne, from there you can reduce it all the way to an alkane, or to a cis-alkene with H2 and Lindlar's catalyst, or to a transalkene with your metal reduction. So some common patterns here, lots and lots of permutations possible here. Well, let's take a look at one. All right, in this example, we are starting with acetylene. And we know we can form carbon-carbon bonds on either side or both if we need to. So, and we're ending up with a much bigger carbon chain than we started with. So the question is, where do these two carbons match up with the carbons in the product? So, and there's a good chance they're simply just the carbons that are still a part of an alkyne. So we know how to make this bond on the left, we know how to make this bond on the right. So that's the most likely scenario. It's not guaranteed for sure, but it's definitely where you should start in any case in such an example. In this case, we can see that we have an OH associated with the right-hand side. It's not on the carbon we're trying to attach to, it's on the next one over, and so that should scream an epoxide of some sort, and we'll figure out how substituted. It doesn't have to just be your general basic epoxide, it could be more complicated. In this case, it's going to have to be, because it's got one extra carbon, so we'll need one extra carbon. But we can see that's an epoxide. On the other side, there's no OH associated. So rather than a ketone aldehyde, rather than an epoxide, it's just simply got to be a 2-carbon alkyl halide involved, being attacked by the acetylide on that side. And if you recall, we said that anytime you want to form an alcohol in one of these acetylide reactions, you've got to do that side, form that carbon-carbon bond second, and it's on the other side that you're going to do first. And again, the key is that anytime you have an alcohol present, it's protic. It will act as an acid if it's ever mixed with an acetylide ion. It would just protonate it, and it would kind of kill the nucleophilic attack you're trying to do. So in this case, we can see we need to add the alkyl halide first. So in this case then, we could, and I'm noticing I'm working this forward, you could definitely work this backwards. But in this case, doing that side first, NaNH2, and again followed with a 2-carbon alkyl halide. And now we'll have 2 carbons added there. So, and then here on the other side, we'll add again NaNH2 to deprotonate this side, form the acetylide. And then we saw we needed this 3-carbon epoxide. And notice that 3-carbon epoxide, once we deprotonate here, form that acetylide, we would preferentially attack the less substituted side. And so in this case, we'd have 1, 2, 3 carbons. Like we said, 1, 2, 3 carbons, and it's the second one in that's still going to be bonded to the oxygen. So second one in, still bonded to the oxygen, and then finally we'd finish that up by adding water simply to protonate the alcohol as it forms. It would be an alkoxide, then we'll protonate it, making the alcohol. This is it. Now, if you want to look at this as step 1 and this is step 2, great. Obviously, step 1 here is comprised of 2 steps on its own, but we'll often combine these just like so. If your professor has a preference, obviously, I defer to whatever they say. They're grading your exams. But in this case, I'm looking at this more of like a 2-step synthesis, but obviously you could look at it as many as a 5-step synthesis, but most of the time, we'd kind of limit this to be kind of analogous to 2 steps. All right, we're going to wrap this up with one challenging example in synthesis here, and start you off with a 4-carbon alkene. The problem is we're going to end up with 6 carbons, and so the question is, where do these 4 carbons match up? Maybe they're these 4 on this end, which would mean we need to make this bond. Another option would be they're these 4 on this end, and we need to make this bond. Or yet another option would be that they're 4 in the middle, these 4, and we would need to make this bond and this bond. So, and in principle, I think I'm probably going to ignore that last example and make that the last thing I check out, because making 1 carbon-carbon bond instead of having to make 2 is definitely easier, and we'll just kind of see how it works out here. So in this case, we're going to need to form an acetylide ion. If we're going from a 4-carbon chain to a 6-carbon chain, we're definitely going to need to form an acetylide ion. We'll figure out what that needs to look like in a little bit, but the question then we should ask ourselves is, how do we form the functional group here? So in this case, if I want to make a ketone, how many different ways do you know how to make a ketone? Well, it turns out you only know one way to make a ketone, and that's to have an alkyne. And that alkyne either needs to be terminal, so 1, 2, 3, 4, 5, 6, or that alkyne could be either just needs to be in this location or this location. One of the carbons of the alkyne has to be the one that ends up being the ketone. So, or it could be here. So one of those is going to be our alkyne here. So 1, 2, 3, 4, 5, 6. If we do it from the second one I've drawn here, so being an internal alkyne, it wouldn't really matter if we used like HgSO4, H2SO4, or if we did hydroboration oxidation like a bulky borane. With an internal alkyne, it doesn't really matter. There's no such thing as Markovnikov or anti-Markovnikov. We do have a problem with that though. So because if we did this, we could form the ketone either here where we want it or here. And so if we use this second one here, we'd also probably get a really decent yield of this ketone as well, probably 50-50 in fact, somewhere probably in that ballpark. So this may not be the best route to go because I do get the desired ketone, but not a great yield. So in this case, if we do the other one, so with this terminal alkyne here, we want to make sure we do this Markovnikov then, and so in this case we specifically want to use mercury sulfate in sulfuric acid. So we do not want to do hydroboration oxidation. And in this case, the major product is when it goes Markovnikov and is the product we're looking for. So we don't have to worry about it competing heavily with any kind of side reaction, at least nothing major. And in this case, the major product is our desired product. This is the route we want to go. And so we want to make this lovely terminal alkyne. That's the way it's looking. And the question is, how do we make that terminal alkyne? Well, in this case, we know how to make this bond right here. So in this case, we make that bond right there by having this alkyne here and then a 1, 2, 3, 4 carbon alkyl halide. So when we do that in step 2, and in step 1 we add NaNH2. So, and that's going to pull that off there. And so in this case, the question is, with these 4 carbons, we're not actually trying to make our alkyne, we're trying to make this alkyl halide. And so in this case, that's what we actually got to funnel our reactant alkene into. And so the question is, how do we get there? Well, with our alkene, to get the bromine there, we actually do that in one step. So I exactly know how to make that with just simply adding HBr and peroxide. This way it goes anti-Markovnikov. The bromine ends up on the less substituted side, the H added on the more substituted side, and that's our synthesis there. So here we've got one step. So then this combination will be the second step, and then we'll have a third step right here. 3-step synthesis. This can be a little bit tricky because rather than making what we're writing in front of the arrow, we're making what's over the arrow, but technically those can be in either location, so it's really kind of arbitrary the way you did this. If I wanted to write this out a little bit different, I could have just again started with my alkene, added the HBr and peroxide to make my alkyl halide in this case, and then we could have just simply added the acetylide already ready-made, already deprotonated. 1, 2, 3, 4, 5. I killed a carbon. So by the way, when you're making carbon-carbon bonds, it's really easy to kill a carbon like I just did, so always count your carbons. So, and then finally we could finish it off with the HgSO4, H2SO4. So if you didn't like the way we did this the first time, you could definitely write it out like this. And again, there's 1 step, 2 steps, 3 steps to our synthesis.